Let's talk about the fundamental counting principle. So sometimes we need to know how many different ways a certain thing can happen. There are 3 basic ways to do this. We can make a list, we can make a tree diagram, or we can use the fundamental counting principle. So let's look at an example where we'll use all 3. You are choosing to wear an outfit to wear. You have a blue shirt, a red shirt, a yellow shirt, a pair of jeans, and a pair of khakis. How many different possible outfits do you have? So if I was trying to list out all of the different options, right, I could start with this blue shirt. And I could say that I could wear the blue shirt with a pair of jeans, or I could wear the blue shirt with the pair of khakis. And then I could move on to the red shirt. I could wear that with jeans, or I could wear that with the khakis. And then last I have that yellow shirt, and I could wear that with jeans, or I could wear the yellow shirt with khakis. Right, my ordered list gives me a good way to see all of the different options. And then I could just count them up. There's 1, 2, 3, 4, 5, 6 different options for the outfits. Now I could also make a tree diagram. The tree diagram has the benefit of it's going to give us all the different options like the list will, but it'll do it a little bit faster. So we have a starting point where we can think of it like our decision. The first decision I have to make is what shirt I'm going to wear. So if I think about that, there were 3 options. I could wear a blue shirt, I could wear a red shirt, or I could wear a yellow shirt. Then after I've decided the shirt, I have to decide on that pair of pants. So I could wear jeans or khakis. And if I chose that red shirt, I have the same option, the jeans or the khakis. And for the yellow shirt, same 2 options, the jeans or the khakis. So here, if I was trying to read an option, I'm going to follow one of these lines, right? So I could say I wore a blue shirt with jeans or a blue shirt with khakis. So you're just following those branches of the tree. And then to find how many options there were, we'd count the different branches. So I have 1, 2, 3, 4, 5, 6 total branches again. Now, if we're using that fundamental counting principle, what that tells us to do is multiply the different number of options we have. So if we think about what's going on, we're really making 2 decisions, right? We're choosing the shirt that we're going to wear, and we're choosing the pants that we're going to wear. For the shirt, I had 3 different options, the blue shirt, the red shirt, or the yellow shirt. For the pants, I had 2 options, the jeans or the khakis. And the fundamental counting principle tells us once we figure out those options for each individual thing, we can multiply them together. So if we do that 3 times 2, that gives us the 6 possible outfits. And notice that's the same answer that we got from the list and from the tree diagram. So the fundamental counting principle has the benefit that it's much faster, but it has the downside that it doesn't actually tell us what all those options are, where with the list and the tree diagram we can see all the different options. So there's 2 formal definitions of the fundamental counting principle that the textbook gives us. They tell us if you can choose one item from a group of m items, and then a second item from a group of n items, then the total number of 2 item choices is m times n. So where we just talked about it, the one item from group of m items, that's like our shirt. We chose one shirt from the 3 possible shirts we had. And then we choose a second item from the group of N items. That was like the pants. We chose one pair of pants from the 2 options that we had, and we multiplied them together. Then the second definition essentially tells us that we can use that fundamental counting principle even when we have more than 2 things. So they tell us that the number of ways in which a series of successive things can occur is found by multiplying the number of ways in which each thing can occur. So let's look at another example. They tell us that the model of car you are thinking of buying comes in 9 exterior colors, 5 interior colors, leather or cloth seats, 3 body styles, and with or without a sunroof. In how many ways can you order your new car? So to help keep track, just like I did before with the shirts and pants, I'm going to draw a line for every decision I need to make. So the first thing they tell me is that we have the 9 exterior colors. So for the exterior colors, we have to choose one of those 9 colors. The next choice we have to make is about the interior colors. They tell me that there's 5 different options there. So I'm going to multiply by 5 because I have to choose one of those 5. Then they tell me that it's leather or cloth seats. So they don't give me a number there, but I have to choose either leather or cloth. So I know there's 2 options, I have to pick one. So I'm going to put that 2 as my number of options for seats. Then they told me there's 3 body styles. So I'm going to multiply by 3 because I have to choose one of those body styles. And then they tell me with or without a sunroof. So the last decision I have to make is, do I want a sunroof? Right, so with or without is those 2 options. Then what I'm going to do is pull up my calculator and multiply. So I have 9 times 5 times 2 times 3 times 2. That tells me that there's 540 different ways to order this car. So let's look at another example. And here we have a few different parts that we have to think through. So they tell us that a pizza can be ordered in 3 sizes with 4 crust choices and 7 choices for toppings. In part A, they ask us how many 1-topping pizzas can be ordered. So if I think about what's going on, I need to choose a size. I'm going to need to choose a crust. And then I'm going to have to choose 1 topping. So they tell me that there's 3 sizes that I have to choose from, that there's 4 crusts that I have to choose from, and that there's 7 choices for the toppings. So when I do that 3 times 4 times 7, that ends up telling me that there's 84 different 1-topping pizzas. If I look at part B, it says how many 2-topping pizzas with the same topping allowed can be ordered. So I still have to choose one of those 3 sizes, and I still have to choose one of those 4 crusts. What's different this time is that there's 2 toppings. So what that's telling me is that I'm going to have to choose my first topping, and then I'm going to have to choose my second topping. So I know there's 7 possible toppings. So for topping number 1, there's going to be 7 options. And then they told me that I can order the same topping. So if I order pepperoni as my first topping, I could say I want double pepperoni, right? I want to order it for my second topping as well. So I still have all 7 options there. So I'm going to do 3 times 4 times 7 times 7. That tells me that there's 588 2-topping pizzas that we could order here, as long as that same topping is allowed. So now let's look at part C. They're asking us how many 2-topping pizzas, where they must be different toppings, can be ordered. So if I think about this, I still have to choose one of the 3 sizes, and I still have to choose one of the 4 crusts. Then, like before, I have my first topping, and then I'm going to have my second topping. So for that first topping, there are still 7 options. I can pick whatever topping I want. But notice they said that they must be different toppings. So if I'm thinking about that second topping, right, one of the toppings is eliminated. If I chose pepperoni as my first topping, then I cannot choose it again for my second topping. So that means I only have 6 options left here. So when I multiply, I have 3 times 4 times 7 times 6. Oh, I missed the 6. 3 times 4 times 7 times 6 gives me 504 different pizzas that are possible. Let's look at the next question. So they tell us if a test has 20 multiple choice problems and each problem has 5 possible answers, in how many ways could a participant answer the questions? So if we think about what's going on, right, we're on question 1 of the test. It's multiple choice and there's 5 possible answers. So I have to choose one of the 5 options. And then because there's 20 multiple choice problems, I'm going to move on to question 2, where I also have to choose one of those 5 options. Then I'm going to move on to question 3, where I have to choose one of those 5 options. Then I'm going to move on to question 4, where I have to choose one of those 5 options. And then it's just going to keep repeating, right? I'm going to move to question 5, where I could pick one of the 5 options. Move to question 6, where I have to pick one of those 5 options. And it's going to keep going that way all the way up until I get to that last question of the test, right? When I'm looking at questions 5 through question 19, I'm thinking about that same thing. So I could go to my calculator and type 5 times 5 times 5 times 5 20 times, but I'm probably going to lose track of how many times I typed it in. So another way to write that is to say 5 to the 20th power. So if I go to my calculator, I'm going to hit 5. Then over on this left-hand side in the middle, I'm going to hit that a to the power of b, and then I'm going to type in 20. So when I do that, that gives me this answer 9.53674316 times 10 to the 13th. So that's our answer in scientific notation. If you want to get an idea of what that number is, right, that times 10 to the 13th is telling you to bump that decimal point to the right 13 spaces. So if I do that, I need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then I'm going to fill in those blank spaces with zeros. So if we put those commas in to help us read this number, right, this is my hundreds place. Right, then this is the thousands period, millions, billions, trillions. So it's over 95 trillion different ways to answer this test. Let's look at another example. They tell us that license plates in a particular state display 3 letters followed by 4 numbers. How many different license plates can be manufactured for this state? So if we think about what's going on, it's got 3 letters followed by 4 numbers. So I'm thinking about my first letter, then I need that second letter, then that third letter. Then it's 4 numbers. So we have the first number, right, the second number, the third number, and I'm running out of room, the 4th number. So if we think about the letters in our English language, there's 26 letters. So there's 26 different options that the first letter could be. They don't tell us anything about repeats, so we're going to assume that repeats are okay. So the second letter could also be 26, and so could the third letter. That could be 26. Now, if we're thinking about the numbers, we're thinking about the numbers 0 through 9. So including 0 and including 9, there's actually 10 different numbers there, or 10 different digits that there could be. There's 10 different digits that the second number could be, and 10 digits that the third number could be, and 10 digits that the fourth number could be. So we can do 26 times 26 times 26 times 10 times 10 times 10 times 10. And if we do that, we get this 175,760,000 different possible license plates. One thing to keep in mind, if you didn't want to have to type everything in, the 26 is 3 times and the 10 is 4 times, you could have said that it's 26 to the third power, because there's 3 26s, times 10 to the fourth power. And if we double check, 26 to the third power times 10 to the fourth power, we get the same exact answer. Let's look at one last problem. They tell us that 5 singers are to perform at a nightclub on a Saturday evening. How many different ways are there to schedule their appearances? So in part A, we're just thinking about the different ways to schedule their appearances. So we're thinking about who's going to sing first, who's going to sing second, who's going to sing third, who's going to sing fourth, and who's going to sing fifth. So if we think about this, if I'm just kind of drawing their names out of a hat, there's 5 possible people that could sing first. And then I'm not going to have the same singer sing twice. So there's only 4 possible options left for who's going to go second. There's only 3 possible options left for who's going to go third. 2 possible options for who's going to go fourth. And then 1 option for who's going to go fifth. So I'm going to do 5 times 4 times 3. Let me try that again. 5 times 4 times 3 times 2 times 1. And that gives us that there's 120 different ways that we could schedule their appearances. Now in part B, we're going to throw one limitation on it. They're saying, what if one of the singers insists on being the last performer of the evening? So if we think about the first, who's going to go second, who's going to go third, who's going to go fourth, and who's going to go fifth, this time I'm actually going to start in that 5th spot. So one person insists on being the last performer. So if I'm agreeing to that, then there's only 1 possible option that I could do there. Then if I think back to the first, well, there's only 4 singers left now. For second, there's 3 singers left. Third, there's 2 singers left. And for the fourth, there's only 1 singer left. So when I do that multiplication, I have 4 times 3 times 2 times 1 times 1, which tells me that now there's only 24 different ways that we could arrange those singers.